So next question 7 part D. If you wondered that why sun appears in a specific color, so here this question is going to address that query. Well, this temperature, it is deeply linked with the temperature. And in fact, in this question, we have to find out the peak wavelength at the 5800 Kelvin temperature, right? So I will explain you, just give you a background concept that how can we find out the wavelength. And well, the sun is a gigantic celestial body, and its radius is given in the same question, which is 700,000 kilometers. This is radius. Okay, and the sun emits a large amount of energy, but according to the modern physics, remember this thing, that this energy that is radiated, okay, it is 3.8 multiplied by 10 power 26 watt joules per second. But this energy is not radiated in one light. In fact, the whole electromagnetic spectrum is radiated from sun into the vacuum. So what I mean to say, that the sun radiates the light in the form of gamma ray. It radiates the form in the form of the radio waves, and in fact it also radiates the light in the form of the visible lights. So in fact, all the lights from the electromagnetic spectrum shares some amount of energy out of this total energy radiated in 1 second. Okay, so if it is clear, then let's see, according to the Wien's law, if you want to find out Wien's law, you can find out the peak wavelength, all right, and the equation for that is lambda max multiplied by the temperature is equals to constant. Okay, now the surface temperature is given in this question, which is 5800 Kelvin. Okay, right? So which wavelength will share the maximum energy part out of this total energy? This deeply related with the wavelength and temperature, right? So you can see that the wavelength, the peak wavelength, why I am saying it's lambda max, I will show it from you, from the graph, right? So it is equals to the Wien's constant divided by temperature, right? So if I put the values, so it is 2.9 multiplied by 10 to the power negative 3 divided by 5800. Okay, so let's see what answer do we get. So dear students, I got 5 multiplied by 10 to the power negative 7 meter. Okay, now you can also write it like 500 nanometer. Okay, now which light has a wavelength 500 nanometer? It is you can say it is a blue green light, or it can also be green yellow light. Okay, because this 500 nanometer is in between the blue green and green yellow light, so that will appear to your eye at this surface temperature. So students, according to the Stephen Boltzmann law, I will just take you a few seconds for this question. The energy, according to Stephen Boltzmann law, and that actually explains you the modern physics concept, that if you take the intensity on the y-axis and the wavelength on the x-axis, then this graph shows you that the energy 3.8 multiplied by 10 to the power 26 watts joules energy in 1 second will not be distributed equally in all the lights. Okay, so in fact, I'm sure you are already aware of that. This is a shape of the graph. All right, this is a curve, Stephen Boltzmann curve. Now notice that the peak of this curve shows us that the light, this wavelength of light, okay, right now whose wavelength is 500 nanometer, which we are calling it peak wavelength or the maximum wavelength. Why we are calling it maximum wavelength? Because at this wavelength, the light coming out of the sun has a maximum intensity, and maximum intensity means that light is carrying maximum energy per second per unit area. Okay, so I hope you understand.